And hello, welcome back YouTube. Welcome to this video of doing this what do you call it? We are doing this series on radiation heat transfer. So today we're going to talk about some more numerical methods. We went through the moment method before. So the idea behind a lot of numerical methods is to reduce all the integral differential part. Okay, in case you missed it, ICYMI. We are trying to reduce a very complex looking a radiation transport equation that looks something like this. Okay, we have this integral differential term. Alright, we have this integral differential term. We are trying to get rid of this scattering term because that makes it a lot harder to solve. So one of the ways to deal with the scattering term is to actually do this thing called, we integrate out the whole thing. We integrate out the whole thing, and we integrate out the angles, and we solve equations based on the integrated stuff. So for example, we were talking about first and second order moments as well as zero order moments, and basically what we have is that we find that the intensity can be expressed as sort of a polynomial. It can be expressed as a polynomial of something like this, where the intensity is as a function of r. R is the position dependent, s is the direction dependent part. So in general, for any moment method, you can decompose this intensity field into this one, the sort of a polynomial, and this is just one term, a direction independent term. Then of course you can decompose the higher order terms into a position dependent part and a direction dependent part. Likewise for the second order moments as well. So basically, what we are doing is that we decompose the radiation intensity field into one part that's a function that is dependent on position and a function that is dependent on direction. So one way we do this is to do spherical harmonics. Okay, and why do we want to go through all the trouble of doing spherical harmonics? Well, one of the reasons is because there's something special we can do to spherical harmonics where we can eliminate a lot of terms and make the equations very simple. I will get to that in a while. But okay, take a look at the form of this equation here. We see here we can express a radiation field in terms of several components of the field. One, of course, is this term, this very generic term, which is this direction independent term, and then we have direction dependent and position dependent and direction dependent term, and we go etc., so on and so forth. Okay, how does this actually come to look like this? So okay, this IML, this one is just the constants that you see in front here. Alright, and this YLM, you can think of it as the direction dependent part, which is again it is dependent on this S and the dot product with S, and then this this is a vector matrix product with SS. So this is actually over here is actually a scalar. It's a series of summation terms, and likewise this is another series of summation terms. So like you see before, the I2RSS is this whole thing all together, and likewise the simpler one, the I1.RS, I1R.S is yet another few summation terms together. So let's take a look. We can just do some addition. We can add a new section here. I'll use this section. Okay, spherical harmonics, and I'll say basic concept. Okay, and I will give this a subsection here. Okay, expanding out the spherical harmonics. Okay, so we have this thing that looks a bit scary here. Okay, not the spherical harmonics, intensity field. Okay, so we have this scary looking thing here, but I'm trying to say that it's not so scary. So do be patient with me as I try to expand out some of this expression here. Let me move my microphone a little, a little bit more of a convenient position. Okay, so let's type out some things. So Control-Shift M for licks. So we have I, R, hat, and then I'll have S there. So this is the radiation field is equals to the sum of going from L equals to 0, going all the way up to infinity, INFTY. Okay, and then you have another sum there. Sum, okay, going from M equals minus L, going up to M equals to L. So we're just going to try and write some of the first few terms out so that it looks a little less abstract. So first one is the R term, and then you have the Y, L, and then M term. So Y, L, M here, these, what you see here are the spherical harmonics. Okay, this is the part where, this is where it gets its name from. So spherical harmonics. Okay, so this is the summation. So let's try and write out at least, let's try writing out from M equals to 1 to, or rather L equals to 1 to L equals to 3, or L equals to 0 to L equals to 3. Okay, so let's see whether we can insert. Okay, so I'm inserting like a vertical space here in licks, so that at least in the document it looks a little bit nicer. Alright, so yeah, I'm going to export as a LaTeX document, so you won't see that. Okay, but anyway, let's expand now. Let's see for L equals to 0. We can try a subsection of sorts. Subsection or subsection. L equals to 0. Let's write. How do we write it? So the terms, the relevant terms are as follows. L equals to 0, right? So we take so we just have L equals to 0. Then we just have this summation. We just have this summation here. So M equals to minus 0 to 0. Now this is a very simple summation. Okay, so I'll just replace everything here by 0. Okay. So what is this? M equals to 0. When you have M equals to 0, this whole summation actually just reduces to the following. Okay, you have I0, Y0, 0. Okay, that's pretty simple. Let's do the next one. Subsection L equals to 1. Okay. Let me put L equals to 0. Let's put L equals to 1 now. These are just indices that you want to kind of get you used to. Alright. Let's do L equals to 1. Then everything in this part will have to be 1. Everything at the bottom will have to be 1. now it goes from m equals to -1 to 1. So now there's a m equals to -1 term, m equals to 0 term, and m equals to 1 term. So let's write. Alright, so there will be 3 terms, so I need to copy and paste this thing 3 times. Okay, so I'll write it here. Okay, so I have 3 terms here, right? So I will just do something like this. Alright, so I don't want all my formulas to go on one space. So let's do m equals to -1 first. Okay, then we have m equals to 0, and then m equals to 1. Okay, hopefully you're seeing some sort of a pattern here. But let's keep going. Now we have L equals to 2. So I will just copy and paste this here and this here. So now L equals to 2. You can see as we go to the higher order terms, it gets more and more complicated, and the number of terms in the summation gets longer and longer, exponentially higher in fact. So we have to change everything at the bottom to m equals to 2. So L equals to 2. Okay, so this is 1 term. Okay, this one is 3 terms. L equals 2 is 5 terms. Alright, so you can see it exponentially growing very fast. So 1, 2, 3, 4, 5. So we have some from -2, then we have -1, and this is 0, and this is 1, and then this is 2. So this is 5 terms. So as you can see, if we keep going, now this one's the L equals to 3 term. Subsection L equals to 3. We can sort of guess already that there is a pattern that comes out. Now this is actually 7 terms. So I'm going to copy again the last time. Okay, so let's do a L equals to 3. And you can see this is an infinite summation. Alright, infinite summation. So again, I'll have to have 2 more terms here. 1 and okay, let's put them at the bottom. Plus, okay, and this. So let's change this at the bottom to 3. And actually, I can just save myself typing space or typing time, because all of these terms are very much still relevant, because you have all the way going from -2, -1, 0, 1, and 2. All you need to add is just these 2 extra terms. So every time you go to a higher order term, you just keep adding 2 terms to the next series. Okay, so basically it's a very, very long summation. Okay, very, very long summation. Alright, a very, very long summation for each of these terms, and it gets more and more complicated as we go up the number of terms. Okay, so basically this is the idea of how these summations are. We can reconstruct this whole field by summing up, the spherical harmonics. Okay, and you kind of give each a weighting factor, so to speak, to each of these spherical harmonics. There. Now, okay, what are spherical harmonics? Okay, Okay, the spherical harmonics are these part called YLM or YML. Alright, yeah, so this is actually a YML or YLM, depending how you want to pronounce it. But yeah, I always learned from my teachers as YLM. Basically, the idea, how does this all come about? Okay, how does it all come about? Okay, this is just a test of game, high and low, yes. Alright, let me select some much nicer. Okay, so picture yourself having sort of a simple harmonic motion, right? Okay. Alright, I want this thing out. Okay, there you go. Let's have picture yourself having simple harmonic motion, and the equation of choice is that, oh, this is very thick. X double dot plus omega square x equals to 0. Now this is the equation of simple harmonic motion. So you sort of have this simple harmonic oscillator kind of equation, and usually the what do you call that? Let me reduce the size. It's so big. Yeah, that's much better. Yes. Let's delete this and you try again. Yeah. So usually we'll have a situation where, okay, the solutions are usually in terms of sines and cosines. Okay, so it's a sine mx, okay, and a cosine mx, or maybe nx, depending on whatever you have. So generally the solution is as so. What the values of m here are, m and n here are, these are determined by the boundary conditions. So okay, let's say we take it to a 2D level. We have the equivalent of the sine and the cosine mx in 2D, and these are called Bessel functions. Okay, so called Bessel functions. Alright, and if we were to go by extension, go to the 3D in spherical coordinates. I mean, I have to qualify that these are in spherical and cylindrical coordinates. You can of course have a box geometry where you have a product of sine or product of cosines as your relevant functions. But in spherical and cylindrical coordinates, they are the spherical harmonics and Bessel functions respectively. So these are the spherical harmonics. Okay, so what is actually inside this YLM? I'll try to do some derivation, not too much, but just do a little bit. Just hopefully to get help you to understand and not be scared away. But if you already know what these are, you can just skip ahead a few videos. But I'm going to continue anyhow. Okay, so remember, what I was trying to share just now is that you have this equation, simple harmonic oscillator equation, and your general solution is somewhat in the form of x equals to some in front there will be some constants and then the sine nx, and there'll be some more constants and there'll be a cosine mx. Alright, so analogous to the spherical harmonics, the an and bm, these actually correspond to this ilm in front, and then the sines and the cosines actually correspond to this ylm. Alright, the spherical harmonics in 3D. So if you're not sure what this ylm is, the simple way to think of it is the sine and cosine waves in 3D. Okay, so that's what we are dealing with here. So yeah, in 3D you can write your oscillation equation a little differently. So instead of d2 by dt square, or d2x dt square, okay, this is an oscillation in time. You can also have oscillations in position. So usually these are oscillations in position, okay, for spherical harmonics, but it can be with respect to time or whatever as well. But usually it's with respect to position that we have this kind of wave going on. So these are with respect to position, so we like to use this Laplacian notation. So instead of this d2 by dt square, we have this Laplacian of x, del square x, and then you have omega square x. Now this is known as the Helmholtz differential equations. Now how do we write del square x in spherical coordinates? You can see, in this this below. You can find on Wolfram online, of course. You'll see what the spherical harmonics actually looks like. Okay, so this looks a little complicated, but I'm going to break down the math a little bit. So this is the Laplacian of x in 3D spherical coordinates. So in this notation, I will take theta to be the polar angle. So it's like, if you think of the Earth is from like North Pole to South Pole, and the phi is the azimuthal angle. So it's like east to west kind of a idea. Okay. Sometimes people like to use phi as the polar angle, theta as the azimuthal angle. That depends on which textbooks you're reading, whether you're using a math textbook or physics textbook. But whichever the notation is, what is important for us to know is which angle represents the polar angle, like going from north to south pole, which is the azimuthal angle, which is going from east to west. Okay. So one common way to solve this 3D Laplacian type of equation is to have this separation of variables. So how do we do separation of variables? Basically, we have x, which is a function of theta, phi, and of course the radius r. So we separate these things out into a function of theta, which is the polar angle, a function of phi, which is the azimuthal angle, and a function of r, which is based on the radius. Again, you can look at Wolfram to elaborate a bit more. So if we were to substitute into the harmonics equation what this thing looks like, it will look like this. Nabla square, or also del square x, equals to minus omega square x. Then you will have a situation where we try to replace x with this expression. This is a product solution. We make this assumption, and for most cases it works. I mean, most of the cases we are going to deal with it works. And the spherical harmonics, for spherical harmonics derivation, that definitely works. So we substitute all of this in, and we take a look. All right, this one is a del by del r. So it will differentiate with respect to r and keep everything else constant. Okay, it'll keep everything else constant. So that means we can factorize out this theta function and this phi function. Now we do the same. Do the same also for this equation here. This one is del by del theta, so we can bring out this phi function and r function. Likewise, for the phi over here, which is the azimuthal angle part, I can bring out this theta and r function. Of course, I'll have the omega square x on the right hand side, which kind of is spilling off the page. So apologize for that, but basically you have x equals to this a function of 3. So you just substitute it all in. So we can factorize out all of this as I was saying just now, and divide throughout by x, or where x equals to the product of this theta, phi, and r functions. Okay, so we'll get something quite simple over here. Unfortunately, we still we are trying to simplify equations so that you have one term here exclusively dependent on r, one term here exclusively dependent on theta, one term here exclusively dependent on phi. Alright, so that is what we are doing here. Alright, so how do we proceed? So first thing first, we can multiply throughout by r squared, and this thing will be now completely dependent on r. This thing will be now completely dependent on r. These two terms are now only dependent on theta and phi. So no problem, we will deal with this part later. Let's separate it out so that we have one part dependent on r and one part dependent on the angles. So how do we then proceed? Well, we have this equation where this partial differential equation where you have theta and phi on here, and you have the r terms here. The only way for this to be solved is to equate the right hand side and left hand side to be a constant. So the only way that both of these can be equal is for both of these to equate to some constant. So we call this constant K1. For example, I can use any other notation as well, but doesn't matter. Alright. You then what you're left with is an ODE for R, and then we can solve for that at the bottom. This is actually an ordinary differential equation for R now, because there are no other variables in here except this big R and then this small r and then this constant. But that's actually not the interesting bit. The interesting bit is actually this part of the equation here, which actually contains the differential equation for spherical harmonics. So where our YLM comes from is actually from this differential equation here. Okay, so what we do is we try to separate this equation out into further two terms. Okay, a further two terms. Okay, so we try to do the same thing what we are doing before, to separate out into one term. Over here, hopefully we have a term exclusively dependent on the polar angle. Over here, we hope to have a term exclusively dependent on the azimuthal angle. So the way to do that is to just multiply by sine squared theta. So we do this, okay, we do this, and then we bring all the theta terms to one side and all the phi terms to one side, which means the azimuthal terms to one side and the polar angle terms to the other side. Alright, so once more, we can separate the left and the right, and for this to equate, both have to equal some constant. Okay, both have to equal some constant in order for this equation to work, and we can call this constant something like minus m squared. Why do we want to do it like that? Because now it makes this azimuthal angle equation relatively easy to solve. You can see here, del 2 phi of del phi squared, this is capital phi anyway, times 1 over phi equals to minus m squared. And if you multiply both sides by this big phi term, it will actually look exactly like a simple harmonic equation. It will look exactly like a simple harmonic equation, and that is actually one part of the spherical harmonics. It is this simple harmonic equation where you have cosine and sine functions here. So this one is pretty trivial. I won't talk too much about it. And of course, the other way you can express it is in terms of imaginary exponential functions, which is you have this some constant cm into exponential i.e. m theta. Okay, the other more the polar angle equation is actually more interesting to solve. Alright, so we have this m squared over here. Okay, we have this m squared over here. We have k1 sine squared theta and all of this here. Alright, so how do we solve it? So we first have to convert this thing into an ordinary differential equation we are familiar with. But for now, I'll stop here. I'll continue more discussion of this ODE, which actually we can convert into Legendre's ODE. I don't know whether I'm pronouncing that right. Legendre polynomials, okay, and Legendre's ODE will be the topic of next few videos. But basically, that's the other part of the spherical harmonics. Where does it come from? Alright, I'm going to stop now. Thanks for watching. I'll see you guys again. Bye-bye.